now that we have holography, anti-de Sitter space, and conformal field theories on the board, I'm ready to get back to the AdS CFT correspondence. And again, maybe just to summarize, make sure we're on the same page. Am I correct then that roughly the conjecture is that the holographic principle can be realized within string theory, and more particularly that a string theoretic bulk in anti-de Sitter space is indistinguishable from a conformal field theory in one less dimension on the boundary of that bulk? Okay, perfect. Then I think the first question that comes to mind that I don't think that we have addressed yet regards this word indistinguishable that I just used. And how is it that entities or processes in the bulk can be translated to entities and processes in the boundary, and vice versa?
Right. So the idea is that there is a kind of dictionary that, given some calculation you do in the boundary, there is some way of doing that calculation in the interior. The dictionary is not obvious and is not complete, so we understand some features of the dictionary, but not everything. So, for example, in certain cases, we expect that the black hole interior should be described from the boundary, but we don't know the precise dictionary. For other things, we know the precise dictionary. So basically, the closer something is to the boundary, the easier it is to describe, and the more precise the dictionary is. So yeah, that's roughly the idea. So the idea is that something that is very close, that is closer to the boundary, is described by a very small object in this conformal field theory. And as it moves away from the boundary towards the interior, it becomes a bigger and bigger object.
Mm. This is totally unrelated, but I'm going to draw it back in a second. But I saw that you have Italian and Argentinian citizenship. Are you from Argentina?
Yeah, I'm from Argentina. But
you
my
just have Italian ancestors?
Yeah, I have Italian ancestors.
Okay. Well, here was where I was leading with that. And so the bulk theory, as we've said, is much less tame than the boundary theory. And I'm going to draw an analogy here to Spanish and English. And so even if, let's say, we're both English speakers and we don't speak Spanish, even if we did have a dictionary that translated from words from English to Spanish, and so we knew what every word in English was, let's say it's the boundary theory, it's the simple one for us. If we translated it into Spanish and we knew the equivalences, we still would have no idea how the Spanish language worked. Is that a rough analogy to? I mean, we know more about Spanish if Spanish is the bulk theory, but even though we know the equivalences, that doesn't completely mean that we understand the bulk theory. Is that
yeah, it's something like that, but it would be like having an incomplete dictionary. Let's say you have an incomplete dictionary, some words missing. So maybe from context, you can try to figure out what they mean, but there will be certain words that you don't know what they mean. So you have to work harder. You have to look at bigger and bigger context in order to figure that out. That's a very rough analogy.
Okay. And then one other thing that I wanted to dig into at the beginning of our conversation, you mentioned that string theory provides us with some very useful toy models for dealing with quantizing gravity. And in the AdS CFT correspondence, that original paper, my understanding is that you worked in a space called AdS 5 by S5. And I'm wondering, I mean, this is not our universe. It's just a model. And I'm wondering why my first question is, I mean, can you explain to us what this space looks like and then why you worked with it for this paper?
Well, string theory is simplest in 10 dimensions. or space-times that are weakly curved in 10 dimensions. I consider this space-time because there is a solution of one of the string theories that is precisely a 5-dimensional sort of anti-de space times a 5-dimensional sphere. So you can think of the 5-dimensional sphere as some external space, and then you have the anti-de Sitter space that we were talking about before. Then that space has many symmetries, and the boundary theory is a 4-dimensional theory. And it's a 4-dimensional theory which is conformal invariant, so it's scale invariant, and again has various other symmetries that we're not going to get into. And it's very similar to the theory that describes quantum chromodynamics. So it's, if you wish, a version of quantum chromodynamics with some particular matter content that makes it scale invariant and have these additional symmetries that I'm not discussing. And so it's a very symmetric, both the bulk and the boundary are very symmetric. And they are the only somehow known theories with those symmetries. So that kind of facilitates. One of the arguments for the correspondence is for the duality is that the two sides have exactly the same symmetries. And this 4-dimensional theory had been studied before as because of these symmetries and various nice properties that it displays, like duality between electric and magnetic charges and so on. So that. Well, maybe I should. I'm doubting whether to get into the precise symmetries of this theory or not, but it has a symmetry that is called supersymmetry. It's a symmetry that relates so-called particles that are called bosons and fermions, and it has the maximal amount of this type of supersymmetries. So the maximal amount that the field theory can have, the quantum field theory can have. And so such theories are very constrained. They're sort of Lagrangian, or the laws of physics for such theories are completely fixed in terms of the choice of so-called gauge group, which is like some number of colors, similar to what happens in chromodynamics. And then there is a coupling constant. So that completely specifies the theory. So it was a particularly simple case. And then later people found some other examples, well, in various dimensions. So even in the original paper, I had also examples in other dimensions. But this example is kind of the simplest in certain sense because of the many symmetries it has. And is one for which a lot of calculations were done, and there is a lot of precise relationship. Well, many things were checked. Let me just try to explain one of them. So according to this, so in theories that are like chromodynamics, that have a large number of so-called colors, the particles of these theories have a color and an anti-color, and they can form chains where the color of one is correlated with the anti-color of the next, and so on. So they form a kind of necklace of particles, and they behave. These chains behave a bit like strings in the bulk theory, and the same thing happens in ordinary chromodynamics, and where they behave like strings in our 4-dimensional world. But in this case, the strings are in this 5-dimensional anti-de Sitter space, and there were mathematical techniques that were developed in order to show that we can go from these chains that you have at weak coupling in the boundary theory, where each particle moves independently. And as you make the coupling constant stronger, the chains, sort of the motion of these particles becomes more correlated, and in such a way that it can be described by a string that lives in the 5-dimensional, or more precisely 10-dimensional bulk space. And this is something that's been shown mathematically. So it's I would say this is great evidence for this duality. offer the correspondence between the two theories.
Well, there are a lot of things there that I want to ask more about, but the first thing is just at the beginning of your response. Now, and please correct me here if I'm wrong, or just making little mistakes. But restricting ourselves to the five-dimensional anti-de Sitter space for a moment, you said that string theory works best in 10 dimensions, and I believe that M theory works best in 11 dimensions, and my understanding is that for the vibrations of strings and various branes to produce the properties of the particles that we observe in the standard model, they require these extra compact 6-dimensional Calabi-Yau shapes in which to move. And what I'm wondering is how, if the theory requires, or theories require 10 or 11 dimensions in these Calabi-Yau shapes, how the bulk theory can be, well, we don't need to get into the bulk theory yet, but how string theory can be emulated in the 5-dimensional anti-de Sitter space.
Okay, so I think string theory can be used in various ways. When we're talking about trying to reproduce the standard model, that's sort of one objective we might have in order to. It's of course an interesting objective to try to understand the physics of our own real world.
Very good point.
Yes. So now when we are talking about this AdS5 and this duality, this basic example of the duality, we are not trying to reproduce gravitational physics in 4 dimensions with our matter content. We are content with having gravitational physics in 10 dimensions on a space which is AdS5 times S5. So it's a 10-dimensional space-time. It's something we can understand easily, well, relatively easily in string theory. And that's the same as this theory in 4 dimensions, this other theory of particles in 4 dimensions. So before, for example, when I was describing the way that strings emerge from the chain of gluons, the gluons are these particles in this version of chromodynamics. When you have this chain of particles, the chain of particles lives in 4 dimensions, but the string that they describe lives in 10 dimensions. That the fact that it's 10, it's related to the particular set of particles that we have. We have gluons and then some other fermions and scalar fields.
Right. And when you say that reproducing the standard model is only one use of string theory, is this also an allusion and maybe implicit reference to the multiverse, and that some string theorists would like to be able to model all possible universes in string theory?
Yeah, that's right. So it might be that for understanding aspects of cosmology, we need to consider not just our own 4-dimensional world, but many other possibilities. Here, that's true, but it's, again, orthogonal to the discussion. So this is one example of the duality, and it uses this particular universe. We could have other examples which use 4-dimensional anti-de Sitter instead of 5-dimensional anti-de Sitter. There are various things we could do, and people have studied all these other possibilities. It's a large number of other possibilities. We don't understand the full set. I mean, we cannot give a complete list of anti-de Sitter spaces where the duality works. We think it should work for all of them, but we don't have even a complete list of possibilities. So I should perhaps say something at this point which is related to string theory and a bit orthogonal to the quantum gravity discussion. So I mentioned in the beginning of the interview that string theory originated as a theory of strong interactions, and this had its origin in the fact that strings were observed in particle collisions. So strings are things that exist in nature, and they were observed in particle collisions at colliders. And when experiments were done at higher energies, it was realized that these strings were somehow made out of gluons, some other more elementary four-dimensional particles. But this shows that, first of all, that strings are real. There is a version of strings that exists. Second, it was realized that these strings would be weakly interacting and more similar to the strings of string theory if you took the number of colors to be very big. So instead of 3, very large. And already perhaps 3 is fairly large for these purposes. And so people had the question of what kind of string theory describes these strings that arise from four-dimensional gauge theories, right? And it wasn't clear that it was the same as the 10-dimensional string. It was something, there seemed to be a contradiction because the strings we understood are in 10 or more dimensions, and these other strings seem to live in 4 dimensions. But it was realized by Polyakov that these strings really should be viewed as living in at least one more dimension. This basic example of the duality is a concrete realization of this idea that the strings of chromodynamics live in one more dimension. This idea is 5, or really 10 dimensions in this case, live in more dimensions. And it's a concrete realization of this idea that the strings that are similar to the strings of strong interactions are actually connected to the ordinary strings of that we were using for quantum gravity. So now we could say, well, let's forget about quantum gravity. We could say, well, if my interest is, if you're a researcher just interested in 4-dimensional theories, but you are interested in understanding theories, for example, at strong coupling, then you can use this 10-dimensional description with AdS 5 times S5 as a toy model for a strongly coupled field theory. And it was used in this way. So from this point of view, you don't care that the interior is not the standard model and so on. What you care in that case is that the boundary theory is somewhat similar to the standard model. You're not trying to, similar at least to the theory of strong interactions.
I know that this is orthogonal, as you said, but it's really important and really interesting. And I was at first surprised to hear you say that strings were observed in colliders because, well, before I say because, but they're not the strings of string theory. They're the gluon necklaces you were referring to when we were talking about conformal field theory.
Yes, but the duality shows that they are not so different.
The duality may show that they're not so different, but my understanding is that the general physics community does not think that strings have been observed. The string theoretic strings have been observed.
No, they don't. But probably that's a true statement. But I think intellectually they are rather similar. And I think people have been trying to take the large N limit of quantum chromodynamics, so large N, and find some strings there and see how different or similar they are. So the correct statement is that if you replace quantum chromodynamics by another theory that you add extra matter fields, then it becomes this highly supersymmetric version of quantum chromodynamics. And then for that version, the strings are really the strings of string theory. So they are closely related. They're not completely unrelated. So from a theoretical point of view, I could say, well, and those strings are the strings of colliders are relativistic strings. They are, similar to the strings of string theory.
When you say relativistic strings, you're referring to the 4 dimensions?
Yes. So okay. Let me try to explain the difference between violin string and the strings of string theory. Okay, both are strings. The the violin string has a very large mass per unit length compared to its tension. So mc squared, well, or mc, so it's much larger than the tension. For that reason, the waves that propagate along a violin string go at a speed less than the speed of light. So a relativistic string is one where the mass per unit length is essentially the same as the tension, up to factors of the speed of light and so on. And so then for those strings, a perturbation, for example, would move at the speed of light along the string. And the ones that are observed in the collider are the same as the second one that I mentioned, and those are also the ones of string theory like that. There could be also something people call cosmic strings, which would also have this property. They might arise not as they must arise as some kind of soliton in quantum field theory. So so that's what I would call a relativistic string. The strings of fundamental string theory, or maybe you should say weakly coupled string theory, the ones that are easy to understand, are strings that interact little when they cross, so they can just cross without reconnecting very easily.
And my understanding is that cosmic strings can really grow to, or have grown to, cosmic proportions. And if I'm recalling correctly, Ed Witten has a very funny quote where he says something to the effect that how funny would it be to confirm string theory by looking through a telescope rather than something like the LHC.
Right. Yeah. So that's a possibility. So it could be that cosmic strings could be either made of other particles, like solitons of field theory, or they could be also fundamental strings. And I think it was referring to the fact that they could be fundamental strings, and they would have slightly different properties. So this fact that when they crossed, the probability of reconnection could be different. But so far, cosmic strings have not been observed. But it's one of the things people are looking for. And would be nice if the universe is kind enough to provide us with very big fundamental strings. It would be really wonderful.
Well, returning to from our tangent to the main thread of our discussion, and one of the last things you said was that you chose to use the 5-dimensional anti-de Sitter space for the correspondence because it was tame. The symmetries were neatly aligned between it and the conformal field theory, the boundary theory, and so on. But then this raises the question, if one of the goals is to explain our universe, what ensures the relevance of this result, or maybe not ensures, it's still a conjecture, but what leads you to believe that there is, or there might be, a corresponding correspondence between our potentially 11-dimensional bulk and the boundary?
Right. I think the idea would be that there would be a similar correspondence, perhaps. It's not clear where the boundary would be in our universe. So the most natural boundary that our universe would have would be in the very far future that will expand. And in some sense, there is a boundary which is 3-dimensional Euclidean space. And so maybe there is another.
The universe is 4-dimensional?
Yeah, the universe is 4-dimensional, and it has a 3-dimensional boundary in the far future. So you can think of that as some surface that at some moment in time in the very far future. So before we were talking about the boundary as some place in space very far away. In an expanding universe, we would say, well, some spatial region, some moment in time at very late times. And it could be that our 4-dimensional universe can be defined in terms of certain statistical system in 3 dimensions. So field theory in 3 dimensions. But we don't know any example that has a gravity, Einstein gravity dual. That there are examples that are related to weird theories of gravity, strange theories of gravity, with lots of massless higher spin particles, where this seems to be true. So one would need to generalize the correspondence to this case. This could be one way in which it could be generalized. The other possibility is that there is some kind of quantum mechanical system that describes our observations in all the way up to the cosmological horizon. That's another possibility that people are thinking about. But we don't have some examples. So in the AdS case, in some sense, we were lucky by this discovery of Polchinski of these objects called D-branes that acted as bridges between the field theory and the gravity theory. And we don't have similar objects or they are not known, that could help us in this cosmological situation.
The first possibility you mentioned with the boundary being far in the future, it's hard for me to wrap my mind around this, particularly because wouldn't the bulk, if we're still using this hologram metaphor, wouldn't the bulk have to be a projection into the past for us to exist now? If there is no boundary now and the boundary is in the future, but the bulk is a projection from the future.
Well, I mean, in general relativity, the universe, it continues to the future, and you could consider what will happen in the future. We somehow are at some point within that four-dimensional universe. We're at some point in time, and we're.
If you're taking like a block universe sort of picture. If you're taking sort of like a block universe sort of picture, everything exists.
Yeah, so it has this for and we are living in some kind of slice at some moment in time. So we would be some object in that boundary. So I don't want to talk too much about it because we don't have concrete examples.
Sure.
But there isn't a completely obvious reason why it could not be true.
But then maybe we don't have to keep talking about this too much more, but just to wrap my head around it, just as there are.
Let me make one little point about this, which is the fact that if such a description existed, then we would have something well defined in the future, and the fact that there is a singularity in the past or something like that, which just means that the bulk four-dimensional picture ceases to emerge somehow in the bulk, but there is still a well-defined description in the infinite future for anything we could calculate at that point. I should mention that it looks like this description is a little weird, but when we look at the very early universe, we are somehow looking at the projection of. We're looking at the similar slice, if you wish, or similar moment in time. So the early universe, there were things that were happening in the very early universe that left their imprints in the universe we observe today. So, for example, when we say that the inflation predicted some fluctuations and imprinted some fluctuations, which we now see through the cosmic microwave background, that surface that we see that we see with fluctuations far away, is a bit like this. The surface of the far future of the early universe. So from the point of view of the early universe, that is in the far future. And by looking at the correlations, the statistics of fluctuations, whether it's up or down, and how they are distributed in space, we can figure out what was happening in the very early universe. So we can say, well, there were particles being created, or maybe there could be interactions between particles, and so on. So we can reconstruct, in principle, we can reconstruct the physics of that very early universe by looking at this sort of cosmological observables.
So when we look at a star that's in the past, what we're seeing is part of, it might be thought of as the surface of a rough sphere of photons whose surface is determined by the geodesics that those photons traveled.
Right. Yeah, for the case of a star, the translation is a little more direct, but
well, very, very interesting. But what I was going to ask before you added that point, and I'm sorry for harping on this since you've mentioned that we don't have a fully developed theory for this, but I was wondering if one way of making sense of this boundary being in the future but projecting into the past is, I mean, we're familiar with non-local interactions in space from quantum mechanics through entanglement, for instance. It's not that much of a stretch to think that there could be non-local interactions through time in the case of the boundary, and the boundary being in the future and the bulk not.
yeah, in quantum mechanics, I wouldn't describe them as interactions. So we have correlations which are non-local and sort of stronger than classical correlations. So that's entanglement. And yeah, so in the AdS case, there is a radial direction, a space-like direction that is emergent from the boundary, right? And the idea is that similarly in the future there would be an emergent direction which now will be time-like, would be time. So yeah, but we don't have very good ideas for how this would happen, or what properties. So that you would need perhaps some special properties about this statistical field theory to have a time emerge. Yeah, I should mention, you mentioned entanglement, and one of the themes of recent developments is to highlight the importance of entanglement in the construction of space-time from the boundary theory. So you have in the boundary theory, the vacuum is a highly entangled state, and the bulk reflects some properties of this entanglement.
Mm-hmm. Right. Eric Verlinde, I know, is working on emergent gravity that emerges from entanglement entropy.
Yes, and there is actually this been, so we mentioned in the very beginning this formulas of Bekenstein for the entropy of black holes, and now we have a new formula that was originally developed by Ryun Takayanagi and then improved by various other people, that calculates another kind of entropy of a black hole. So the entropy that von Neumann discussed is an entropy that calculates the sort of quantum information available or contained within a system. So if you have a quantum system, sometimes it might be in a so-called mixed state, not in a pure state. And there's a quantity that characterizes how mixed, how many possible quantum states you have. And that is the von Neumann entropy, or sometimes called fine-grained entropy. Now, this is in general different than the sort of Boltzmann entropy or thermodynamic entropy of a system, especially when you are out of equilibrium. So for describing, for example, a collapsing black hole or situations like this which are out of equilibrium, you get the difference between these two entropies. And we have a sort of area formula for each of them, and it's been quite useful to think about this direction. So in the same way that the Bekenstein formula told us many things about black holes, this other formula is also telling us interesting things about the black hole, and in particular about the black hole interior, because the area is also, the formula also computes the entropy as some area, but it's not the area of the horizon, it's the area of some surface in the interior that you need to determine. So it's telling you some information about the interior.
Do these two conceptions conflict at all, or are they simpatico?
No, they are compatible with each other. So it's just that normally most physicists have heard only about, they know one definition of the entropy, and normally this distinction between the two types of entropy is not definitely it's not relevant for a system in a thermal equilibrium, but that has equilibrated over a very long time. But it is quite relevant for systems that are out of equilibrium.
Well, that's very interesting because then it's quite like the AdS CFT correspondence in that two descriptions of the same phenomena can be useful in different contexts.
Um, yeah, well, this is more elementary, I would say. So even for simple systems, I mean, this idea of thinking about the two entropies is something that people have discussed. They discuss a lot in the condensed matter physics literature and so on. And it's important when you consider out of equilibrium situations.
I know that you wanted to get away from this, but this is, I promise, the last question that I will ask about the boundary. And you can also totally decline to answer it because it opens up a huge can of worms. But I could conceivably understand a boundary far in the future. But at one point, you said there might be a boundary infinitely far in the future. And that's difficult for me to wrap my mind around physically.
Well, let's say infinitely means very far.
Okay.
Yeah, there are no infinities in physics. It's always some very far. You know, it's
Yeah,
some
because
idealization. It's always some idealization. It means that it's very far compared to other timescales that you are considering in the problem.
okay, sure. No, that makes more sense because I always hear that whenever an infinity crops up in a physics equation, it means that something has gone wrong somewhere.
Right, right. No, this is not. This is just simply reflects an idealization. It means much larger than other things.